All right. Mic check 1 2. Welcome, ladies and gentlemen, to another series of tutorials with me, Aubrey. This is going to be a very interesting lesson. We started a series earlier. We were looking at a tutorial from Moivre'S College of Education. This is analysis of a complex variable, also known as complex analysis. Prior to this video, we have done part 1, where we looked at questions 1 and 2. I showed how to go about solving question 1 and how to go about question 2. In part 2 of this video, I looked at how you can go about solving question 3 and question 4. Okay, we looked at how we can solve question 3 and question 4, and this is part 3. And in part 3, we are looking at question 5. Now, question 5 is very interesting because we are proving the Moivres theorem by 1. We are going to prove this by the exponential function. Then secondly, we're going to prove it by mathematical induction. And hopefully this part of the video will also catch question number 6. Then I think in part 4 we'll look at question number 7 and 8, then part and so on and so forth. So I'll break it down into short videos like that, so that we can have a better understanding. So now subscribe to the channel, leave a like so that the video is suggested to other people. So let's dive into the question. So what does the Moivre's theorem state? Excuse me. So the Moivre's theorem states that if you have cos theta plus I sine theta to the power n let's see, this is equal to cos n theta plus I sine n theta, like that. So the n basically drops. The n goes down there and down there. So this is what the Moivre's theorem states, and we're going to prove this by firstly the exponential function. So let me dive into that. So let me just drag this. I'll drag it right here. Okay, well, I've just dragged it on my workspace here so that I just have enough room to work out. So proof by exponential functions, proof by exponential functions, we're going to use by Euler's theorem, is it Euler or Euler's? Depends. By Euler's theorem, we know that e to the I theta is equal to cos theta plus I sine theta. So this is Euler's theorem, and that is for exponential functions. This is what we're going to use to prove. So by Euler's formula, we know that this is that. So it means that if we raise everything, raising the equation to the power n, raise the equation to the power n, so now if we raise everything to the power n, what are we going to have? We're going to have we're going to have e to the I theta, everything raised to the power n, and what we do to the left hand side we also do to the right hand side, cos theta plus I sine theta, everything raised to the power n. Okay, so this is what we have, and we know by exponential rules, by exponential rules, a to the power b to the power c is equals to a to the power b times c. So meaning that Euler's formula can now be written as e to the I n theta is equal to cos theta plus I sine theta raised to the power n. 1. Okay, so let's keep that equation for now. So that is our equation now, equation 1 for now. Then we'll go to equation 2. Equation 2, we're saying we're using Euler's formula. We know that e to the I theta is equal to cos theta plus I sine theta. If we let theta to be equal to some random variable, let's say let theta be equal to some variable k, then our Euler's formula becomes e to the ik being equal to cos k plus I sine k. Okay, and being from linear algebra, we can say this k is some integer, positive or negative, we don't know. So it is just some integer like that. So we are going to have that. So yeah, so now if we let again k be, since k is just a number, if we let k to be equals to n theta, okay, if we let k equals to n theta, how will Euler's formula become? This will be e to the I. Where there is k here, we're putting n theta being equal to, where there is k here, we're putting n theta cos n theta, okay, plus I, where there is k here, we're putting n theta sine n theta, okay, and we see this is our equation 2. We see that equation 2 and equation 1, we have this part which are the same. Just zoom out, see that okay, from equation 1, this is, where is our equation 1? This is our equation 1. This part and this part are the same, so we can equate these sides of the equation and these sides of the equation, and we see that what we are going to have, let me just move this here, equating equation 1 and 2, okay, equating equation 1 and 2, okay, equating equation 1 and 2, we see that we're going to have, what are we going to have? Okay, we are seeing that this part, see that this part, we can start with that part, which is cos, let me see, let me start from here, cos theta plus I sine theta to the power n will be equal to this part, okay, which is cos n theta plus I sine n theta. So hence proved. So this is how you prove the what's this? This is how you prove the Moivres by the exponential functions. So yeah, so now let's go on and prove using using mathematical induction. So again, I'm just going to clear that. You can follow the video to write to clear that. So proof by mathematical induction. You know that mathematical induction takes 3 steps for you to prove. You need to take 3 steps for you to prove. So we are proving, remember what we are proving. Let me just write it here. We are proving that cos theta plus I sine theta to the power n is equals to cos theta, cos n theta, cos n theta plus I sine n theta plus I sine n theta. And we are proving this by mathematical induction. Mathematical induction. So we should take 3 steps to prove this. The first step, we know step 1, we need to show that it is true for n equals to 1. Show true for n equals to 1 for every n equals to 1. So when n is 1, so we have we start with our formula. First of all, we write our formula down, the formula we are proving. So we are proving cos theta plus I sine theta raised to the power n is equals to cos n theta plus I sine n theta. So now we say when n is equals to 1, will the statement be true when n is equals to 1? When n is equals to 1, we're going to have cos theta plus I sine theta raised to the power 1, okay, is equals to cos 1 theta plus I, this is times sine I sine 1 times theta. Just write there 1 times theta. And we see that this raised to the power 1 is just the same one. So we see that we are going to have cos theta plus I sine theta will be equals to cos, what is 1 times theta? It will just be theta plus I sine theta. So true for n equals to 1. True for n equals to 1. So this is true for n equals to 1. So as you can see, these are the same basically. So we go on to step 2. Now step 2, you find that even in most books, they don't recognize this step because we are just replacing n with k. So step 2, replacing n with k. So step 2, replace n with k. This is our assumption. We are assuming that n is equals to k. Assume that n is equals to k. Okay, and what we're going to have is cos theta plus I sine theta to the power k is equals to cos k theta plus I sine k theta. And as you can see, we've just replaced where there was n, we've just replaced with k. So here there was n, we've replaced with k. Here there is nk, and here there is nk. So yeah, so now we go on to step 3, which is the hardest step, or let me say where you need to do some work. So step 3, we are show that the statement will be true for n equals to k plus 1. All right, so we need to show that the statement will be true for n equals to k plus 1. So what we do here is we're going to write first what we are proving. We're proving cos theta plus I sine theta to the power n is equal to cos n theta plus I sine n theta. Okay, then when n is equals to k, when n is equals to k plus 1, when n is equals to k plus 1, what are we going to have? Let me just pull it up like that. So we are replacing wherever there is n, we are putting k plus 1, k plus 1, k plus 1. So we are going to have cos theta plus I sine theta to the power n. We're replacing with k plus 1. So this is k plus 1 is equal to cos plus I. Okay, let me just put. So where there is n, we're putting k plus 1 times theta, like that. Okay. Plus, let me just put this in parentheses like that. Okay. Plus I plus I sine, open brackets like that. Again, that would be k plus 1 times theta, like that. So now in this step, we need to show that the left hand side can produce the right hand side, or the right hand side can produce the left hand side. So it is up to you. So you need to show that the left hand side can produce the right hand side, or that the right hand side can produce the left hand side. So I'm going to choose, you can choose either way. So I'm going to choose this side of the equation to produce this side of the equation. Okay, I'm going to choose that. All right, so here we are going to use the left hand side to produce the right hand side. And how we are going to do that is we said cos theta plus I. This can be written as this using exponential properties. Remember, if we had powers adding, it means that their bases were multiplying. So we are using all those principles. And from step 2, remember that cos theta plus I sin theta to the power k was equals to cos k theta plus I sin k theta. So in this vein, we're going to pick this equation. So meaning that on this part of the equation, we can replace this right here, so that we are going to have, cos k theta plus I sin k theta times cos theta plus I sin theta. All right, so you are going to have that. Now you need to start multiplying. So you multiply this times that, this times that. How we multiply? So to save some time, I'm going to just quickly multiply this. All right, so after you multiply and distribute, you're going to have something like this after you separate the real parts and the imaginary parts. And what you can see here is that this is coming from an identity you might know, cos k theta, cos theta. So this is actually coming from the identity cos k theta plus theta. Okay, if you remember that identity, when you distribute this times that, this time you will get that. Remember that the identity plus I, and this is coming from the identity of sine. So this is coming from the identity sine k theta plus theta. Okay, so we know that this is this, so this is equals to that, and we see that this is actually, when we factor out the theta, we're going to have cos k plus 1 theta. You can put the parentheses, k plus I sine k plus 1. We can factor out the theta there. We'll put out the parentheses. We see that this is actually equal to the right hand side. So this is actually equal to the right hand side. So let me just draw out here. Let me pull out. Okay, I'm not sure if you'll be able to see that, but we see that actually we have used the left hand side. We have used the left hand side to come up with this, which is actually equal to the right hand side, as you can see there. So we say true. All right, so here we can conclude that the statement is true for n equals to k plus 1 simply because we are able to produce the left hand side using the right hand side, or the right hand side using the left hand side. All right, so from here we make our conclusion. We'll say since the statement was true for n equals to 1, since the statement was true for n equals to 1, n equals to k, and n equals to k plus 1, so the statement will be true for all values of n. The statement will be true So the statement will be true for all values of n. So, and that's basically it. So let's dive into part 2. I mean part 4 now. All right, so part 4, have a good day.